Okay, so before we begin, just a quick thing for timing purposes. If there are any questions besides strictly clarification questions, we ask that you keep them to the end just because they can make us deviate off track. And since it's confusing enough as it is, if we can keep that to the end, that would be really appreciated. Okay, now let's begin. It's 3008 and aliens have landed on Earth. In order to survive, they're visiting schools around the country, like Pingree, trying to pick up their necessities. Unfortunately, they've set their sights on Pingree. And Pingree students, being the valiant and honorable kids they are, have set up barricades. They're blocking all the road access that aliens can use to access Pingree. However, they forgot one very important route. The route that leads from Mr. Connor's house in the woods to the doors of Pingree. In forgetting this route, they allow the aliens to access Pingree, so the Pingree have their key to survival. Drug researchers today are confronted with similar issues as they see cancer cells develop new ways to access key characteristics that are essential to their survival.
Our drug Farydak tries to block the one other route that cancer may utilize to help its progression. Our drug Farydak will inhibit the inhibition of tumor suppressor genes. By modifying epigenetics, we can reactivate these tumor suppressor genes, thus inducing apoptosis and stopping tumor growth.
Can you say the inhibit thing again?
Okay, Farydak will inhibit the inhibition of tumor suppressor genes. Do you want the next part too?
No, I'm good.
Alright, the cancer our drug is trying to treat is called multiple myeloma. Multiple myeloma is a cancer in the plasma cells, which are cells found in the bone marrow. It is an immune cell, and what it does is attempt to fight infection. But an over or excessive proliferation of these cells can lead to an unbalance in the immune system and make your body susceptible to infection. Thus, although it's not very prevalent, only about just under 2% of all cancer cases, it's still very hard to treat, and over our lifetime, we each have a 0.7% chance of developing multiple myeloma. Alright, abnormal epigenetic patterns in cancer. Okay, so epigenetics, which is just another word for how tightly the DNA is wrapped around the histone, can do many different things towards cancer. Although we focus mainly on DNA mutation in cancer, epigenetics also play a key role in how cancer may progress. In multiple myeloma, certain tumor suppressor genes are inhibited, and cancer can use these epigenetic mechanisms to thus inflict more damage upon the body.
So basically, epigenetic mechanisms are just ways that they change how tightly the DNA is wrapped around the histone, and by changing how tightly it's wrapped, it will change whether the DNA is accessible for transcription or not. Okay, so this isn't our drug yet, this is just background information to help you understand what our drug actually does. So right here we have the two different states of DNA wrapping. We have the tight one on the top and the looser version at the bottom. So before we look through the diagram, I'm just going to label some things. These blue things are the histones. The bolded black line is the DNA wrapped around the histone. And these thinner black lines are going to be the histone tails. And the histone tails are just a chain of amino acids that kind of stick out and wiggle from the histone. And what happens to these histone tails is they can be modified in different ways that impact how tightly the DNA is wrapped around the histone. You guys all got that in the video, right? Okay. So can anybody tell me a difference they observe between the top and the bottom? Maybe like spot the difference. Tommy?
For one, the bottom has sparkier histone.
Okay, so they're more spread apart, right? What else? Jared?
The yellow things are binding to the histone.
Right, so at the bottom one, we see these little yellow circles. Those things represent acetyl groups. And what's so important about acetyl groups is that they make the DNA accessible for transcription. The way I like to remember it is A for A, acetyl group is for accessible. So how this works is actually just charges. This isn't really necessary for you to remember, but if you want the scientific explanation, the lysine up here is positively charged, so it will interact tightly with the DNA, which is negatively charged. Down here, the acetyl group holds a negative charge, so negative, negative repel, open transcription. Are we good there? So who can tell me what the difference between the top and the bottom is? Jackie.
The bottom is nucleated.
Mm-hmm.
The DNA is like wrapped less tightly. It's like more functional.
Exactly. Okay.
Okay, so what our cancer multiple myeloma does is it takes the cell from a state of where gene expression occurs to a state where no gene expression occurs. thus inhibiting tumor suppressor genes. It does this through the employment of molecules called HDACs. HDACs are molecules that remove or deacetylate these histones and remove the acetyl groups, thus making the DNA more tightly wound around the histone, thus stopping gene expression from occurring. Because transcription machinery can't work when the DNA is too tightly wound. Is that good? Everyone good? Okay. So multiple myeloma, the cancer, takes this state of the cell from a state of gene expression, such as expressing tumor suppressors, to a state of no gene expression through molecules known as HDACs. HDACs remove these acetyl groups, thus making the DNA more tightly wound around the histones. And the more tighter wound they are, the transcription can't occur because there's no room for transcription machinery to work.
So it's basically the converse of what you were just saying before. Okay, so overall, the big takeaway from this slide, what we want you to remember, is that these enzymes called HDACs, they will inhibit the gene expression of the segment of DNA that's wrapped around the histone of that they're modifying. So if an HDAC is targeting the histone maybe 4, then the gene that's wrapped around that histone 4 will not be expressed because it's too tightly wound. Do we get that? Yes.
So does it wrap around specific histones for specific traits?
Are you asking if the DNA, the sequences of DNA are always wrapped around the same histone?
Like if you wrap it more tightly around a certain histone, that changes like one particular gene, I guess.
There are segments of the DNA that code for certain proteins, and in this case, yes, this gene segment of P53 or P21 is being tightly wound around the histone.
Yeah, Billy?
Are the HDACs upregulated in your cancer?
I'm not sure if they're upregulated, but they do have abnormal activity, so they like deacetylate the wrong sections of the histone. Yes, Jason.
Are HDACs found in normal cells as well as cancer cells?
Yes, they're a part of normal regulation of gene expression. Okay. So, moving on. If we know that HDACs and histone deacetylases are part of how we regulate gene expression, then scientists want to see if they can kind of interfere with this process and stop the silencing of tumor suppressor genes in multiple myeloma. So, one drug that's capable of this inhibition of HDACs is Farydak. So, how Farydak works is kind of explained by the structure. So, we'll look down here. Basically, highlighted in purple right here is called the zinc binding region. And what this region does, it's kind of like the active site of our drug. It basically absorbs or chelates a zinc ion inside the HDAC's active site. So some HDACs are dependent on having this little zinc ion in them, so without it they can't properly function. So Farydak will take away this ion, rendering the HDAC ineffective. So, can someone tell me what the what Farydak does to the HDAC? What?
So the specific section of the Farydak binds to the specific section of the HDAC, which like messes up the zinc active site.
Yeah, exactly. Exactly what Fad said. Okay. So now drug developers have found a way to stop HDACs, and from the prior slide, we know that HDAC stops gene expression, so double negative, we know that Farydak will allow gene expression to happen. It will reawaken those silenced genes. Okay, so here's our fat rat, or a mechanistic proof. So basically, if there's something that will inhibit the removal of a different something, one way to show that that initial something works, let me start over. Okay, so if a drug inhibits the removal of something, then we should see an increase of that something in the presence of the drug. Do you get that logic? Raise your hand if you get it. Thumbs? Okay, good. So, what researchers did is they performed a Western blot test in multiple myeloma cells that were treated with Farydak. So, over here you see the hours that the cell has been exposed to our drug, and after this just control. You see that the level of acetylated histone 4 over time increases. Yes, Mr. D.
No, 5 minutes.
Okay. And over here, you just see that this is a dose-dependent relationship. Got it? Yes, Jason.
How does that show a dose-dependent relationship?
As the level of the drug increases, that's how much you administer, the level of acetylation also increases. Yes?
So you're increasing more.
Right.
Okay, sorry.
Okay. Now over here, we're seeing that gene expression is actually altered by this increase of acetylation. So remember before how we talked about increased acetylation means more accessible? This is just the proof that shows that this increase of acetylation actually results in real changes in gene expression. So here we see that the levels of P53 and P21 in the cells are increased when cells are treated with Farydak.
Okay, our drug Farydak was approved by the FDA in February of this year. It is used to treat multiple myeloma only if 2 prior therapies for this cancer have been tried and failed. Our drug Farydak works best in tandem with bortezomib, a proteasome inhibitor. A proteasome is just a protein degradation pathway, and an immunomodulatory agent, dexamethasone, which basically means it stabilizes or helps balance your immune system. Okay, here is a graph of the extended progression-free survival probability rate. On the left side, the y-axis represents the progression-free survival probability in percentage, and the x-axis represents the time in months after diagnosis. As you can see here, after diagnosis, the black line with the black squares represents the patients who took Farydak plus bortezomib and dexamethasone, and the dotted line with triangles represents the placebo with dexamethasone and bortezomib. As you can see here, those who took Farydak have a significantly increased survival rate. From 8 to 12 months, we see around a 25% increase in survival probability.
So all this is showing that when you take Farydak with 2 other drugs, it's more effective than just the other 2 drugs on its own. Okay, and one reason for this possible increase of progression-free survival is their synergistic relationship between bortezomib and Farydak. So as Michael mentioned before, bortezomib is a proteasome inhibitor, and we learned proteasomes as the Death Star this year. Remember, they're kind of like a trash can or recycling bin for proteins, so they'll break down the amino acids so they can be recycled in the cell. So bortezomib inhibits this kind of protein degradation, and Farydak, on the other hand, inhibits the other type of protein degradation, lysosomal degradation. So how Farydak accomplishes this inhibition is again by inhibiting one of those HDAC molecules, HDAC6 specifically. What this enzyme is responsible for in lysosomal degradation is it assists in the transport of the misfolded protein to the lysosome. So by inhibiting this car, if you're trying to drive your trash to the trash plant, then the trash can't happen. You know what I mean? So what's super important about this dual inhibition of protein degradation pathways is that cells need to be able to properly dispose of proteins in order to survive. And if they're unable to do so, they'll activate apoptosis. So, questions here? Who can tell me what inhibits proteasomal degradation? Is it bortezomib or Farydak? You have a 50-50 shot.
Bortezomib.
Good. So bortezomib inhibits proteasomal degradation. Okay, so what's the other one?
Farydak.
Farydak, good. And Farydak will do this by inhibiting the car that you use to take your trash to the recycling plant. The HDAC6. Do we have that? Thumbs? Anywhere? Okay. What are you confused about?
The cars, the trash going to the recycling bin now.
Okay. Okay, so you know when you have a lot of recycling stuff that you need to bring to the facility to get it sorted out? Your dad will load it all into the car. The car will drive your trash to the trash center. So by stopping the car, you're stopping the recycling of your goods.
Okay.
Yes.
Analogy, which is the car, which is the trash?
So the trash is the misfolded protein, and the car will be the entire the complex that transports that misfolded protein, which includes HDAC6. Okay. So by inhibiting both pathways of degradation, there's a complete blockage to ping read. Before, this was unoccupied, the invader could access ping read through this route, but now we see Farydak occupy that position, blocking lysosomal degradation. Over here, we see that bortezomib is blocking proteasomal degradation. So this results in a complete block of protein degradation, and the cell cannot access any kind of protein degradation, so they will induce apoptosis. Thumbs? Everyone? Okay.
Okay, Farydak upregulates tumor suppressor genes such as P53 and P21, thus slowing tumor growth through induction of apoptosis. Farydak also stops lysosomal protein degradation, and when proteins can't be degraded, it sends a signal to the cell that something's wrong and it should induce apoptosis. With these two abilities, we can definitely slow down tumor growth and also extend patients' lives.
Thank you.